Hi there. I'm going to be giving an update on the It's Live project. It's been a while, so we thought it was about time to get something new out there. The It's Live project is a large collaboration between NASA Jet Propulsion Lab, Alaska Satellite Facility, the National Snow and Ice and Data Center, University of Alaska Fairbanks, and the University of Colorado Boulder. The It's Live project provides three primary products: land ice velocity, land ice elevation change, and ice front position. So here we're looking at the land ice velocity. This covers all glaciers outside of the ice sheets and the ice sheets themselves. We also have an altimetry product, which provides elevation change of the grounded ice and then also changes in ice shelf thickness. We will soon have a product for the Greenland ice sheet that is under review. And lastly, we provide ice front positions. We have annual ice front positions for the Antarctic ice sheet and monthly ice front positions for Greenland. Okay, for the rest of the presentation, I'm really going to be focusing on the velocity products. The It's Live team has put in a huge amount of work over the last year, and there's some pretty exciting updates. The first is that the system is now near real time. So that means within hours of an image being acquired, the It's Live system receives a notification which sets off a process where the It's Live machinery goes, searches the past archive, and identifies all of those images that it can use to generate velocity fields too, using the new image that was just acquired. The lowest level data that we provide to the user is called a velocity granule. This is the velocity field generated from two images. And for any location on the Earth, there may be hundreds of thousands of granules for a single point on the Earth. So it can be difficult to work with, but we have some solutions to that that we'll talk to in the next slides. Um, the data, the velocity granules themselves contain a significant amount of noise. And the way the It's Life project is able to beat down this noise and extract the most subtle signals of glacier behavior is simply by acquiring so many granules that we can beat down the noise. That's really the motto of the It's Life project, is just do it again, do it again, do it again until you can beat down the noise and extract the most subtle signals. There's a lot of known issues with the data. We're only able to correct these in post-processing. And so I recommend for any user that's going to work with the raw data that they go and read the known issues document that's on the It's Live homepage. Okay, another thing we should talk about is how the data is derived. And so if you haven't worked with this kind of data before, you might have the intuition that you're looking at instantaneous ice velocity, but you're not. You're really looking at the velocity integrated over the period of the two images. So how much displacement occurred between image one and image two. And so I'll just quickly explain that here. If you look at the right-hand figure, you'll see that there's the blue line. Is what it would look like if you put a GPS at this location. You'd see this very high temporal frequency change in velocity. Now, when we're measuring velocity from space, all we see is the total displacement that occurred between the two images. And so that is those black solid lines. And you typically, when you plot these, you'll just plot it at the location of the black dot. And so you really need to remember that when you're looking at this data, it is not instantaneous velocity, it is the total displacement measured between the two images. So on the bottom panel of that figure, that is cumulative displacement for the figure just above. And what is happening here is when you acquire an image at time one and an image at time two, and then you look for the displacement that occurred between those two images, you get the average velocity over that time. So that adds a complexity to working with the data that's fairly unique to this data set. So we generate all of these granules, and in some locations, there's hundreds of thousands of granules for a single pixel. So a huge amount of data, which can make it really cumbersome to work with. So the first thing we do is we chop the world up into 100 kilometer by 100 kilometer rectangles, and we create data cubes. So we create these ZAR data cubes where we put all of the granule information in a consistent format, and it's optimized for time series access. So this makes it just so much easier to work with the data. You access it as a single file, uh, and then you're off and running. You can access all the data that exists there. The one issue with the data cubes is that they're very expensive for us to update. And so we update the data cubes only a couple times a year because of the cost. So if you're interested in something that happened yesterday, you're going to have to go look at the granules. The data will be there, but you're going to have to work with the raw granules. Now, if you don't care about the immediacy of the data, I really recommend that you work with the data cubes, which will give you access to all of the raw data without having to manage that many files. Okay, so now we have all of the data put into these data cubes, and that allows us to work with the data much easier. So the first thing we do is we apply some ML algorithms to filter out the noise in the data, and then we apply some least squares fitting that accounts for the heterogeneity and the temporal sampling to give us a best estimate of the annual mean velocity, and then also the climatological mean velocity, the climatological acceleration, and the climatological seasonality. And so I'm saying climatological because we only have a single estimate of acceleration, a single estimate for seasonal amplitude, and a single estimate of seasonal phase. Uh, Once the data is gone through all of this filtering, it's much cleaner to work with, much lower data volumes. And so if you're not interested in really specific events that occurred over short periods of time, I recommend that you go and work with the composites or the mosaics, which we'll talk about in a minute. This will just make your life a lot easier because we've already done all of the noise filtering for you and the fitting, which really improves the quality of the product. So we have all of these composites around the world. They're all in their local projections. So at the poles, they're in a polar stereographic projection. In the lower latitudes, they're in a UTM zone. So if you want to look at a whole region, this can be a little bit cumbersome to work with because um, we're working with a vector quantity. So these values are actually pointing in a direction. And so when you open up a composite, it's pointing, the X is in the local X direction and the Y is in the local Y direction. And so when you go between two different projections, that meaning of X and meaning of Y change. So to make it easier for our users, we create these mosaics. We do this for all the major ice regions on Earth. And we project the vectors into the proper projection. So it just makes the data much easier to work with. So if you're doing kind of regional scale analysis, this is really the data set that you want to be working with. Now, we only generate these for areas with significant ice coverage, but there's lots of places on the planet where you'll have, like little clusters of glaciers that it's just not worth going and generating a full mosaic for. So for those regions, the composites exist, so you can get all of the annual averages, the trends, the seasonality, but they're not included in the mosaics. So if there's a region that you're interested in, and you don't see a mosaic for it, just go back to the composites and you'll find it. So one example is the subantarctic islands. Okay, so let's look at the data. On the top figure, we're looking at the seasonality. And so what's plotted here is the phase or the timing of the velocity peak. It is plotted with color. And the transparency is being scaled by the amplitude of the seasonal cycle. So where the transparency is low and the color is green, that means that we have a strong seasonal peak around October or November. So this is directly from the Mosaic product. So if you're interested for your region, you can go and grab this data. It's just sitting there for you to plot. On the bottom figure is what the data looks like in time series form for the X that's in the above figure. So what we're looking at in the magenta color is the raw granule data. And then plotted over top is that least squares fit that we're generating when we're creating the composites. So this is the annual values with the climatological seasonality plotted over top. And you can see that you get a very clean signal from that fit that matches the observations well. But you're going to miss some things like the very steep peak in velocity around 2021. So if you're interested in those types of things, you have to go back to the raw data. But if you're interested in the general characteristics of the glacier, you should be good working with the the composites, and the mosaics. Okay, let's talk data access. We have a web tool that has just been updated, and it's much more user-friendly and intuitive to access the data. So you can access all sorts of different data sets. So you can access the mosaics, the composites, the cubes, the granules. If you go and look at the mosaics, there's also associated QGIS projects. You can download one of those QGIS projects, open it in QGIS, and it will populate all of the annual mosaics and the composite. So you can go explore the data. You can download the data as a netcdf or as geotiffs for the mosaics, or you can find links to the raw granules and the cubes. There's even an option that if you click on any glacier, it will plot the time series at that location, which is pretty cool. You can also just go and access the data in the AWS Open Bucket. You can just go browse the bucket. It's Live is sponsored by AWS Open Data, so all of our data is in an open bucket. There's no cost to access the data, and you can just go poke around and see the data that's there. So this is super helpful if you're interested in some of the parameters that we use when we run AutoRift to generate the velocities, or some of the ancillary data that we use, like land masks, ice masks, water masks, those types of things. You can go use those, and they might be helpful for your research. And lastly, this is my favorite tool. Okay, so this is the brainchild of Mark Fanstock, and this is a tool that allows you to go and explore those data cubes with a slippy map of the Earth. And so you can just lay down points on the Earth, and it will go and instantaneously retrieve all of the velocity data for these locations. And so on the right-hand side is showing an example of this. I've just gone and laid down 3 points. You can see the latitude and longitude of those points. The time series is plotted just below the map. You can see that there was a giant surge that occurred on this glacier sometime after 2025, no, 2015. This is a really cool tool just to get oriented, to see if the types of signals that you're interested in exist there, to understand the characteristics of the glacier and the data before you go and dive in and actually download the data and start working with it more programmatically. On the right-hand side is a slider. This allows you to move around what time integration you're interested in. So this has to do with what I was talking about before, about how the data is generated. So if you just want to look at short interval data that looks more like an instantaneous time series, you can scale that slider to the left-hand side. If you want to look more at low noise annual averages, you can slide the slider to the right. And the cool thing about this web tool is everything that you're doing in the tool is being recorded in the URL. So in this example that I have here, those 3 points are being recorded in the URL, and the time separation that I've selected is also being recorded in the URL. So if you follow the QR code that I have there, it will take you to this exact map, and then you can start moving these points around yourself and exploring maybe where the surge started or where it ended, or you can go explore an entirely new location. But the cool thing is you can just share this with your colleagues. You go, you find something interesting, cut and paste the URL and send it to them in an email. They open it up on their computer, and they're looking at exactly what you're looking at, and then they can start interactively playing with the data. One cool feature that we're actively working on, and we hope to have rolled out early in the new year, is we're going to be overlaying or provide an option to overlay the annual values with the climatological seasonality plotted over top. This will really improve the understanding of the data, because there's lots of locations where you lay down a marker and it just looks purely like noise. But that's just simply because you're not able to do the noise filtering and data averaging to extract the underlying signal. So then you go and you plop the model fit over top, and you start to see signals much clearer. There's a lot more resources on our homepage, itslive.nasa.jpl.gov. I recommend that you go look there. There's a known issues document that you should certainly read. There's links to a Python package, a MATLAB package, and a Julia package that will make it much easier to work with the data. Go out there, play with the data, make new discoveries. The whole goal of It's Live is simply to accelerate glaciological research, and so we are always excited when we see other people using the data and making discoveries of their own.